Okay, this question is about the algebra of complex numbers. The hope is that most of you will have gone through this. If you haven't, it doesn't matter. We will take this a bit slowly, especially for the first part. Part 1 is just basic algebra of complex numbers. Part 2 will require you to remember a few things here and there, fundamental theorem of algebra, a bit of Vieta's formulas. You don't need it, but it makes life easier for this question. And part C, we will need to use Moivre's theorem to be able to find the roots of the cubic function. All right, all the functions or the equations, in the second case, that equation, the quartic equation, is a complex number. The same thing with part C. These are all complex numbers, polynomials. All right, so let's see how we go about this question. Okay, so part 1 of the question requires us to find the complex number z, given that it is made up of 3 different complex numbers, z1 being 3 plus 2j, z2 being 4 minus 3j, z3 being 1 plus 2j. And before I go on, if you're an engineering student, you know, especially electrical engineering, we use letter j there to represent the complex number. That is to say that j is the square root of -1. If you are a diploma student, IB diploma, and other courses of mathematics, where we tend to use letter I to represent the complex, the square root of -1. So letter J and letter I are used to represent the same thing. So I'm going to use J because the student who asked this question is an engineering student, of electrical engineering student, who wanted to know how to go through the problem. Okay, so to answer this question, we'll take this easy. We'll start by just simplifying the numerator there, then the denominator, then we will simplify the full fraction, and then we'll add z2. All right. The easiest way, of course, to solve this is by using polar complex numbers. Converting this to polar form makes life much easier. But let's go through this using a rectangular form. All right. Or the Cartesian form of the complex number, because I think that is what is expected of the student. This question is not easy to solve. You can solve it without a calculator, but it takes a bit of time. So we will try to go through it without using a calculator. It takes time, and it's not really necessary to work it without a calculator. It's just a waste of time. It's just simple processing. So let's start. We'll start by solving that numerator there, z1 times z3. Okay. So to simplify that, z1 times z3, we just take those values and we multiply them together. 3 times 1. So this is 3 times 1, which is just 3, then 3 times 2j, which is 6j, then we have 2j times 1, which is plus 2j, and we have 2j plus, multiplied by 2j, which is 4j squared, which is minus 4, not minus 4j. 4j squared is -4, and so this ends up being 3 minus 4 is -1 plus 8j, like that. And so the simple form of simplifying that, if we open that bracket, we get -1 plus 8j. And so that is what this is, right? Minus 1 plus 8j. The second thing we do is we simplify the denominator there. If we simplify that, that's just adding the 2 complex numbers. We add them algebraically the same way we add in normal algebra. So 3 plus 2j plus 1 plus 2j is simply 4. 3 plus 1 is 4. 2j plus 2j is 4j. So therefore 4 plus 4j is what we get for the denominator there. Next thing we want to do is now to simplify the two, combine the two together. So if we're going to combine the two together, we're going to make use of the product of conjugates to ensure that the denominator is not a complex number. So right now the denominator is a complex number, 4 plus 4j. So we are replacing that with its value and this also with its value. And so to get rid of complex number in the denominator, we multiply by the conjugate of 4 plus 4j, and the conjugate of 4 plus 4j is 4 minus 4j. So multiply and divide by 4 minus 4j there. If we multiply the numerator in the same way that we did it earlier, we will end up with that result there. So just try this yourself, multiply them the way we did this one here, and you should be able to see that we get minus 4 plus 4j plus that. And if you simplify this, you end up with 28 plus 36j over 32. Please notice that this becomes 32, the denominator, if we multiply that and that to conjugate complex numbers, then the result is just going to be a real number, in this case 32. Okay, so this is what we get. We can simplify this by dividing by 4. We get 7 plus 9j over 8. And that is what we now add to z2 there. So if we add z2, I have now simplified this by dividing top and bottom by 4. If we add this together, we end up with 39 over 8 minus 15 over 8j, and that is this simplified. So this is just simple complex number algebra. We did not use a calculator, but you could use a calculator for this if this is a calculator paper. All right, let's go to part B of this question. Right, so part B says that you are given a complex number, a complex equation, basically a polynomial equation, z power 4 plus 2z power 3 plus 6z squared plus 8z plus 8 equals 0. So that is a complex polynomial equation, and you're told that one of the roots of the complex equation is minus 1 plus j, and you are asked to find the other roots. First question is, how many other roots are there? And to answer that question, we go to the algebra, the fundamental theorem of algebra, which says that a polynomial of order n has exactly n roots. So a polynomial equation, so Pn of x or of z, so it could be an equation in terms of x. This one is in terms of z. So I could write here that a polynomial equation, I can say f of z equals 0, where n here refers to the order of the polynomial. In our case, the order is 4. So P4 of z equals 0 is a polynomial of order 4. A polynomial equation of order n has exactly n roots. So our equation has an order of 4, so we expect that there are 4 roots to this equation. So we are going to find 4 roots. We already have one, so then we are left to find 3 roots of the 4. So first fact that we need to know is the fundamental theorem of algebra, and we've said by that fundamental theorem we know that we expect to have 4 roots because this is a polynomial of 4th degree or of 4th order. Okay? Now, the first root has been given as -1 plus j. We need the other 3. One of the other 3 we can already find using the second rule. And the second rule is that if a polynomial is such that its coefficients are all real numbers, so the coefficient here is a real number 1, the coefficient of z power 4 is 1, the coefficient of z power 3 is 2, the coefficient of z power 2 is 6. So you can see all the coefficients together with the constant there are real numbers. In this case, they are in fact integers. It doesn't matter, they just need to be real numbers. If that is the case, then if this is a root of this polynomial, then the conjugate of z1 must also be a root of the polynomial. That's what this says, okay? So the second fact, so this the first fact is that we expect to have 4 roots, and we've already found Z1, so we only need to find Z2, Z3, and Z4. So Z1 is already here. So by point number 2, if a complex number happens to be a root of this polynomial, all right, then its conjugate must also be a root of that same polynomial. This is only true if the coefficients of the polynomial are all real numbers. So in this case, we have real numbers. So since one of the roots is -1 plus j, the conjugate of this must also be a root, which is to say that this is -1 plus j, so -1 minus j must also be a root of this polynomial. It is true because this is a polynomial with real number coefficients, okay? So number 2, there it is, that if the coefficient of a polynomial equation are all real numbers, then all complex roots come in conjugate pairs. So this must have its conjugate pair as also being a root. So there are 4 roots, and this is complex, so its conjugate is also complex. The other 2 may be real numbers, but they may also be complex roots, okay? So let's find those other roots. So by this point number 2, we know the second root already, and that second root, we will call it Z2, is going to be -1 minus j, because that is the conjugate of this one, okay? So since Z1 is a complex root, its conjugate is also a complex root, and the conjugate is Z2, which is -1 minus j. All right, that's point number 2. Point number 3, so now we have 2 roots, we need just 2 more. Point number 3, we now use what we refer to as Vieta's formulas, or Vieta's formula, and in my class we usually compress the Vieta's formula into a simple equation, which I'm putting here now. So this refers to Vieta's formula. If you go to topic 3, you will find a discussion of the Vieta's formula there on how we determine that the sum of all there are 4 roots of this equation, and if we add all the 4 roots, we should get -2. And where do I get -2? It is the negative of the second term here. Okay, so the second term is 2, so the negative of that, if we add all the roots, we should get the negative of that number there. All right, and if we multiply all the 4 roots, we should get that term there, which is 8. Okay, so go back and take a look at how the discussion on this. This should make sense. Otherwise, we just go on. So if that's the case, we already know Z1 and Z2. What we are going to do, let's see if we can get Z3 and Z4. So the sum of all the 4 roots must be -2, and the product of the 4 roots must be 8. Okay, let the remaining roots be a plus bj. Let's assume that they are also a pair of, they are a conjugate pair as well, so that one is a plus bj and the other one is a minus bj. If that's not the case, that will come out clearly when we determine the values of a and b. So we don't need to worry about whether we are making a correct assumption or not. So let's just that be the case. Then in that case, then going by this rule, the sum of the 4 roots must be -2. So if we do that, let's add the 4 roots. All right, which is to say Z1 was, I think, -1 plus j, that's Z1. Z2 is -1 minus j, and Z3 is a plus bj. Z4 is a minus bj. If we add all that, we should get -2. Let's simplify that. As you can see, -1 and -1. This is positive j and negative j, so these 2 are going to cancel. Similarly, bj and negative bj are going to cancel, and we end up with 2a minus 2 is -2, like that. And so clearly the value of a is 0. Okay, we are still left to find the value of b. All right, in order to find Z3 and Z4, we know that a is 0 here. So what is the value of b? So now we go to the second rule there, that the product of the roots must be positive 8. If we do that, I'll keep my a there so that we find the value of b. Okay, so the product of the root means z1 times z2 times z3 times z4 must be equal to 8. We already know that a is 0, so I can simply get rid of it. And I have the conjugate pair multiplied together. You should be able to see that if you multiply this and this, you should get 2. All right, so therefore we get 2 into bj into negative bj. So bj times negative bj is minus b squared j squared, but j squared is negative 1, so that becomes plus b squared. All right, and so we get 2b squared equals 8, and therefore b is plus or minus 2. So we know the value of b as well. So one of the value of b is negative 2, the other one is positive 2. So clearly the z3 is going to be 2j, and z4 is going to be negative 2j. So they also turn out to be conjugate pairs, okay? And therefore the other 3 roots of this polynomial must be, the second one is minus 1 minus j, which was the conjugate of the one that was given. The third root must be 2j, and the fourth root must be minus 2j. There is another way we could answer this question, of course, and that is by working with factors, turning these into factors, but that just makes life sometimes a little longer. So this works well when you have polynomials with higher orders like this. It is usually better to work with Vieta's formula. Let me know if you need additional explanation on this. Otherwise, let's move on to the next part. Part C requires us to find the root of the equation z cubed plus 1 minus j root 3 equals 0. So in order to solve this, now this is also a polynomial equation, of course. It is a polynomial equation of order 3. But now notice that the constant term, all this is that this term does not contain z on it. Because of that, we can say that the constant term is a complex number. So it's not like the previous one where the constant and the coefficients were all real numbers. Here now our constant is a complex number. So the rule about complex roots appearing with their conjugates does not apply in this case. It may still happen that one of the root has got a complex conjugate root, but it's not always the case. Okay, so that rule does not apply anymore. To answer this question, we need to move the constant part to the right. So let's start. We make z power 3 be equal to, this goes to the other side and becomes negative 1. This becomes positive j root 3, like that. The next thing we want to do is to convert this into polar form. All right. To convert it into polar form, we need to find the modulus of the right-hand side, the modulus of this complex right-hand side, and we also need to find its argument. Okay, so the modulus of the complex number is simply, it's like the Pythagoras theorem. So it is basically the square root of 1 squared plus root 3 squared, which is going to be 2. Okay, so a squared, the value of a squared, plus the value of b, ignore the j there, root 3 squared, which is 3, and the negative 1 squared, which is 1, so that is 4. If you find the root, you get 2, and therefore the modulus of the complex number is 2. All right. Secondly, we want to find the argument of the complex number. The argument of the complex number is the angle that the complex number makes with the positive real direction. So if I draw this here, this is called the real axis of the complex number. This is the imaginary axis of the complex number, all right? And the angle that this makes, the angle that the complex number makes. So if we look at our complex number, it says the real part is negative 1. So we move in the negative 1 direction, negative 1 step, and then we move in the positive imaginary direction, so positive root 3. So the complex number falls somewhere here. This is called an Argon diagram. And this angle that our complex number z makes with the positive real axis, this angle here, is what we refer to as the argument of the complex number. We can find the argument of the complex number by thinking about the tangent of this angle, which then turns out to be the same as that. Okay, so therefore it is arctan, we know that is root 3 here, and this is -1. So this angle is arctan or tan inverse of root 3 over -1, which is -root 3. So if we can find that angle, that's the angle here, but then we will take the value that is on the positive side with the real axis. Okay, right, so let's do that. I'm going to erase this. This is called the Argon Diagram, which helps us understand what the argument of the complex number is. Hopefully I've not moved very fast through that. If that's the case, please let me know and I can go through that again with you. No big deal. The argument therefore is the arctan or tan inverse of -root 3. And if you've been studying trigonometry, that should tell you that we are talking about 60 degrees. We are in the second quadrant, like the diagram I just drew there. So that's going to be 60 degrees, but then we are taking the positive from the positive axis there, and therefore we have 120. Okay, so that angle is 120 degrees, which in radians is expressed as 2 pi over 3. Okay, so the angle, also called the argument of this complex number, is 2 pi over 3 radians, or if you like, 120 degrees. Okay, so with this information we can express the right hand side there in polar form, which is basically just r. That means we express this. That means expressing this in the form r c's, I'll write it in full, cosine of 2 pi over 3 plus I sine 2 pi over 3, which we usually just write as r c's of 2 pi over 3. C's here means cosine, this cosine here, and S here for sine, which is this sine here. Okay, so normally we just write it in short because we don't want to keep writing sine and cosine all the time, so we shorten this like this in mathematics. So r c's, and our r is 2, and our argument, which is theta, is 2 pi over 3. Okay, so that is what we have for the polar form. Right, so why do we need to write this in polar form? It is because once we write it in polar form, then we can make use of de Moivre's theorem, which makes life much easier. So let's see. So I can now write my z3, instead of writing it like this, I will express it in polar form, and that is z3 is 2 c's of 2 pi over 3, c's for cosine of 2 pi over 3 plus I sine 2 pi over 3, like that. Okay, and by de Moivre's theorem, if I find the square root of this side, then I have to find the square root of the other side. That is to say, so if I have z power n, if this is equal to r c's of, let's just say theta here, like that, then if I find the square root of this side, I have to find the square root of that side. So z therefore is r c's of theta, and now I put this into bracket and I put 1 over n because we are looking for the nth root. If this is power n, then I have to put power 1 over n. So if this is power 2, then I have to put power half to mean that I'm looking for the square root, and so on. All right, de Moivre's theorem says that this can be expressed as r power 1 over n, this goes to r there, times, and this becomes c's of theta over n. Okay, and we say plus or minus 2 pi k. So this is what de Moivre's theorem says, which is to say now the 1 over n comes and multiplies right there, becomes a multiplication, right? Again, I'm hoping that I'm talking to students who have already been doing this, so it's just a question of solving this problem. So that is de Moivre's theorem, and this is the reason why we needed to change this into this format, because then it becomes easy to find the root of the equation, all right, or the roots of the complex number. But once again, because this is z power 3 by fundamental theorem of algebra, we expect to get 3 different roots, all right? So that is what we have, and when we change it, we find the root, then we are going to write a cube root of 2, because we are finding the cube root of both sides. So zk, or the kth root, is cube root of 2 c's of 2 pi over 9, because there was a third up there that we bring in, so a third, and then we have 2 pi over 3 plus 2 pi k, and if we simplify that, we get this. And so all we have to do now is to substitute. When k is 0, what do we get? So substitute k is 0 there, and we have root of 2, c's of 2 pi over 9. If you enter that into your calculator directly, or the alternative is to leave it in terms of cosine and sine, but it's better to turn it back into that form using your calculator. And if we substitute k of 0, then this is the root that we get. So that's the first root that we get when we substitute a k of 0. If we put k of 1, we get minus 1.18 plus 0.43i. And if we put k of negative 1 there, we get negative 1.18 minus 0.43i, or j, by the way. Once again, remember this is supposed to be a j. For the student who is doing this question, j and I can be used synonymously, all right? And so these are the answers you get. I can see here that 2 of the solutions are conjugate pairs, but the other one is also a complex number, or obviously doesn't have a conjugate pair. All right, so that is how we answer this question. I will see you in the next question. Thank you very much.